All right, folks, so the lesson here today, we're going to take the skills that we learned particularly in section 6.6, where I'm hoping a bit of the takeaway was some work with some unit vectors and new ways to represent our vectors. We were working with coordinates and we were working with components. Now, I would like to address something a little bit before we get going. I realize working in 3-space is it's a little bit new to you folks. So I'm using here, it's the GeoGebra 3D calculator, very handy. I linked it in the announcement yesterday. Where we're working right here, I've plotted 2 points, A and B. A is plotted at 3, 1, 0. B is plotted at 1, 4, 2. Now, these 2 points here, you might notice that may have been a little bit challenging to guess. Those coordinates may have been challenging to guess if I didn't tell you them. And that's because what we're looking at here is a projection of a 3-dimensional space on a 2-dimensional screen, or a 2-dimensional paper when we're writing in our notebooks. So you might notice as I put a little bit of a spin, a little bit of a, let's try and do it slowly, rotation on these points, you'll see that they are flying all over the place as we're moving our axes around. We're rotating around the z-axis right here. And I'm hoping you can see that our A and B points, I'm hoping you can visualize a little bit more their position in space. Now, these 2 points, actually particularly point A, I want to focus on point A. Point A, you'll notice, has a z-coordinate of 0. And point A with a z-coordinate of 0. Let's take a look. I'll stop this rotation. I hope your head doesn't hurt yet. I'll stop this rotation and we'll say, hang on. Point A has only an x component and a y component. It has no z component. It has no z coordinate. So if I set this up, let's see, I can look from above and I can set this up as we are used to seeing our points. Point A here is this is how it would look if we were looking in 2-space with only an x and a y axis. Where here you're noticing our x-axis, the positive x-axis is to the right, the positive y-axis is in the upwards direction. So here, if I showed you just this image, you might say, well, the coordinates of A are 3, 1. Not 3, 1, 0, just 3, 1, because with this particular view, the z-axis is not that obvious. So I'd like you to predict a little bit. If I show point B again, where do you think that's going to show up? Because it has a z component, but with our view right here, we're not noticing any depth in the z-axis. So if I show point B here, you'll see it at 0.14. The 2 here is not identifiable. We're not able to see where these points are on the z-axis. Now I realize in our with our feedback poll yesterday, there was a little bit of confusion. Okay, how does our third component come into play? Well, our third component is actually independent. It is explicit from the first 2 components. The z coordinate is independent of the x and the y coordinates. Now, if I, as you saw before, if I move this to a different view, let's try that out, move it to a different view, then you can see how B has some z depth or a z coordinate to it, because it's not flat. It's not exactly on our xy axes, our xy plane. Now let's take a look instead at point C. All right, point C can be found at 2, 1, and right now, 1. All right, so it's found at 2, 1, 1. Now I'm going to, and I'll stop this right here, and I'm going to play around with my z coordinate. So I'll hit play here, and it should oscillate between +5 and -5. So it goes all the way up, it goes all the way down, and you can see in this view how it's going about. No, the z coordinate does not impact the x or y coordinates, but it does show up differently according to where that z coordinate is. So we'll put a little bit of rotation on this again. We'll try putting some rotation on this again. There we are, and we can see C going up and down, up and down, up and down, but nothing else. All right, now let's take one more look. We're almost done with this exercise right here. We'll take another look at our x and y axes. Where are we? Our positive x, positive y, good. And we'll put here our z-axis straight into your screen, straight out of your screen. And you can see here, although our a value, our z-coordinate, is still oscillating, this C point does not appear to be moving whatsoever, because when we look at it under this view, we don't see z. All right, so I'm hoping you're able to visualize here how our z component works entirely independently from our x and our y coordinates. I'm hoping that was a useful exercise for us to work with. Now we'll close that because my notebook seemed to freeze a few minutes ago when it was open, and we'll try and push forward. Alrighty, so in section 6.6, we found two useful new unit vectors, I, which was 1, 0, and j, which was 0, 1. We could represent these two same vectors in R3 by working with a z-coordinate as well. So here, I could be 1, 0, 0, where still it has a magnitude of 1, and it comes from the origin, where the y-coordinate this time and the z-coordinate are both empty. All right, if that's the case, we could work with j, which shouldn't have a dot. It should only have the harpoon there. There we go. Which could be given by 0, 1, and 0. So these are two unit vectors that we can use when we're working in 3 space. Now, if that's the case, I'm hoping you can see an opening that we have here. We can look forward and we can create another vector, this time in the positive z direction, where we're working with vector k, which is 0, 0, 1, which is the unit vector in the positive z direction. So here you can see we're working, vector I is in the x direction, vector j is in the y direction, and vector k is in the z direction. Fantastic. All right. Now, there's a bit of a diagram here right from your textbook, so we can use these 3 vectors to express any unique vector that we have when we're working in 3 space, in R3. So these allow us to break down our vectors in 3 space into our 3 components. And here you're seeing an analogous breakdown to that which you saw in section 6.6. In section 6.6, we were working in 2 space. So in section 6.6, I'll write in 6.6, we were working with OP was only a b. It only had 2 coordinates, which were given by ai plus bj. This time, we're going to work with ai plus bj plus ck. Fantastic. Now, I'll erase that so we don't get confused as we work forward. I'm hoping you can see here, as we're working in 3 space, I do think our GeoGebra demonstration earlier showed that third direction very well, but you can see third dimension very well, but you can see here our unit vectors, how they're each of length 1, and they're each along the positive axes that they're working with. Now, your textbook really breaks down adding and subtracting these vectors in a nice, I guess, approving sort of way, but we don't really need to break down the how or the why. I'm hoping you could see. I'm hoping your understanding was thorough enough from section 6.6 that you could predict how we would add and subtract vectors in R3. And our approach, frankly, is going to be using the exact same strategy that we used when we were working in R2 in section 6.6. So, oops, there we are. So if we're working with vector A given by QRS, where Q is the x coordinate, R is the y coordinate, and S is the z coordinate, and vector B, which is given by TUV as its coordinates, then A plus B, if we're working with that, then we're going to add the coordinates independently. So that means our x coordinates from A and B both get added together. That means our y coordinates from A and B, so here are y coordinates from A, our y coordinate from B, they both combine, they add to bring us our y coordinate for A plus B. And likewise, our z coordinates, S and V, will combine. We'll look at their sum for the z coordinate of A plus B. If we're looking at these in components, we can see the breakdown in the same manner. So our number of, really, our scalar multiple going in front of our positive x unit vector, which is vector I. For A is Q. For B, we're working with T. So that means that the the scalar multiple that we're working with for a plus b is going to be q plus t. Nice and straightforward, and I'm hoping you can see the pattern that we're working with right here. Now, since we can work with those components, let's get a little bit of practice here. So we'll work if a is equal to 3, 2, negative 2, and b is equal to 0, 5, 7. Then let's try writing them in terms of their components. Well, vector a, all right, vector a, its x-coordinate is 3. And that means it has 3 times the unit vector I. So a is equal to 3 times I plus 2 times j. Plus, and here's the new part, now that we're in section 6.7, we have a z-coordinates. Oops, so minus 2 times k. Fantastic. So what I encourage you to do is come up with the coordinates vector for vector b. Pause the video, try that out, and come back to check your work. Good, so we should be working here with no I component, but 5 times j and 7 times k. Fantastic. All right, now let's work with that was part A. Now let's work with part B, where we're going to add these vectors together using them in component form. Okay, if we're working in components, this is the form we're working with. So if I'm trying to work with A plus B, then I'm working with vector A, which is 3 times I plus 2 times j, minus 2 times k. And then I'm going to add vector b, which is 5 times j plus 7 times k. Fantastic. All right, if that's the case, then I can take advantage of my commutative and associative properties here, and I can rearrange these. So I'm working with 3 times I plus 2 times j plus 5 times j, where I'm grabbing here from vector b, minus 2 times vector k plus 7 times vector k. Fantastic. Now, all right, so I can associate these as I wish. I have 3 times vector I plus, and then I'll work with these two together, plus 2 plus 5 times vector j, plus here, negative 2 plus 7, where, there we are, negative 2 plus 7 times vector k. Fantastic. Now I can simplify. All right, so I'm working with 3 times I plus 7j plus 5k. It looks like my computer is struggling a little bit, but we made it there. Fantastic. All right, now let's work with part C, where we can subtract these using their coordinate forms. So I'm working with A minus B. All right, so then I'm working with 3 times 2 times negative 2, and I'm subtracting vector b, which is 0, 5, 7. Fantastic. Now, if I'm using the same patterns that we used in section 6.6, then my x-coordinate of a minus b can be given by 3 minus 0. All right, my y-coordinate can be given by 2 minus 5. I'm working here with my y-coordinates. And then my z-coordinate, I'll be working with my z-coordinates. There we are. There's my cursor. We'll move this over. Good. We're working with negative 2 minus 7. Fantastic. So I'm working here, and I have 3, negative 3, and negative 2 minus 7. That's negative 9. Fantastic work, folks. All right, let's look forward to example 2. Example 2, we're working with, finding a sum and a difference of these, frankly, because we're evaluating this expression. Now, a minus b plus c, if I'm going to handle something like that, then I need a, b, and c to be given all in coordinates or all in components. Now, you can see a and b are given in coordinates, whereas c is given in components. So I'll encourage you to pause the video here and convert them all as you wish, whether you prefer to work in components or if you prefer to work with their coordinates. Try it out. You should be able to handle something like this on your own. When I upload this to the classroom, I'll have the solution here, but I don't think we'll go over it in the video here. All right, but what we will do in the video is we'll break down a little bit of magnitudes, where we're going to find a way to come up with the magnitude of a three-dimensional vector. So I'm working here. I have I have vector OP, which goes from the origin to point P, which is given by the coordinates A, B, and C. We don't know much about A, B, and C. All right, now, if that's the case, then it's our goal to come up with the length of this pink vector in here. Now, okay, if that's all well and great. Now, if I consider vector A, which goes from the origin to point A, and I consider from the origin to point A, and I consider vector B, which goes from the origin to point B, and I consider vector C, which goes from the origin to point C. That's all well and good. What if I consider their magnitudes? Well, their magnitudes would be nice and simple, right? The magnitude of vector OA, or of, let's just call it vector A for simplicity. The magnitude of vector A, bear with me here. Yeah, you know what? I apologize. Taking a bit of time. The magnitude of vector OA can be given by just the magnitude of point A, of the coordinate here. All right, the magnitude of vector OB could be given by the magnitude of vector B, and the magnitude of vector OC could be given by the magnitude of vector C. Nice and straightforward stuff right here. All right, now if that's the case, if I'm coming up with the magnitude of this pink vector, then what I'm going to need to do is use my Pythagorean theorem using these two vectors here. Because these two vectors, along with, maybe highlighting would be more helpful here, these two vectors, along with vector OP, these are the vectors that create a right-angled triangle, so my Pythagorean theorem will be useful there. Well, that's all well and great, but I don't actually have the length of those vectors yet, right? So I'll need to come up with the vector OD in order to do this first. So vector OD right here. All right, how can I come up with that? Well, you might notice vector OD is the hypotenuse of this right-angled triangle down here. All right, so I can take advantage of this right-angled triangle, and that is, this is vector OA. Let's see, vector OA and vector AD, which is actually equivalent. So let's write OA, sorry, bear with me, folks. OA plus OD. All right, that's true. Now, vector OD is equivalent to vector OB because I can see that they are they're equivalent across the way here. Fantastic. So if that's the case, if OD is equal to OB, then I know sorry, folks, I've written this incorrectly, and I'm hoping it won't. I'd rather not edit this out, so that's okay. We'll share our our work in here. It's not OD I'm looking at across here. It's AD. AD. So AD is equal to OB. Fantastic. And if that's the case, then that means that the magnitude of OD is going to be equal to the magnitude of OA, which we've written as the magnitude of A, plus the magnitude of AD, and AD is equal to OB, so plus the magnitude of B. But we know how this works. We can't just add them. We have to square them and take their square root. That's from our Pythagorean theorem. So if that's the case, well done us. We're on our way there. And you know what? In fact, I'll write this in another form with the squared over here. So OD squared is equal to A squared plus B squared. Fantastic. Now let's get into our yellow triangle right in here. So we're working with our yellow triangle, and we're trying to find the magnitude of vector OP. Well, according to our Pythagorean theorem, the magnitude of vector OP, and actually we'll square it for the smoothness of our theorem here, the magnitude of vector OP squared is going to be equal to the magnitude of vector OD squared plus the magnitude of vector dp. dp. Well, hang on. Do we have any equivalent vectors to dp? Yes, we do. In fact, we have dp right here is an equivalent vector. Let's move that over. We'll see if this works there. Oh, I was close. This vector is equivalent to the vector up here, vector C. Let's put our yellow highlighted triangle back. We're trying it. That's okay. I'm sure this is beneficial video. There we go. So let's write that logic in. So dp is equal to vector OC. And vector OC we give by vector C right here. So that means we're working down here with vector OD. We're almost there, folks. OD squared plus vector OC squared. And in fact, again, we called that vector C. So let's do that for just to clean it up a little bit. Plus vector C squared. Great. So if you've come along with me thus far, that's great. If you've needed to rewind a couple of times throughout this explanation, that's okay too. And lastly, we need to look right here. So we have OD squared. Do we know anything about OD squared? Yes, we do. Vector OD squared can be given by the sum of the squares of vectors A and B. So we'll use that logic, we'll substitute that in, and vector OP, the magnitude of vector OP squared, can be given by the magnitude of vector A squared plus the magnitude of vector B squared plus the magnitude of vector C squared. And what that means is, here we are, we finally made it. The magnitude of vector OP can be given by the square root of vector A, the magnitude of A squared, plus the magnitude of vector B squared, plus the magnitude of vector C all squared. Well done, folks. So if you were able to follow that, that means when we're working in 3 space, our Pythagorean theorem holds as long as we add in the square of our third coordinate. So if that's the case, let's try and use that logic for example 3 here, and then I will let you go. I think this is, yes, it's our last example. If we have vector v given by the coordinates 3, 5, 7, then the magnitude of vector b, according to what we just found, can be given by, the magnitude of vector b can be given by the square root of 3 squared plus 5 squared plus 7 squared. It's that easy. All right, well, I know that's the square root of 3 squared, that's 9, plus 5 squared, that's 25, plus 7 squared, that's 49. So I'm working here. I have 74 plus 9. I'm working with the square root of 83. Can I break that down anymore? No, I cannot. That is the magnitude of vector b. Fantastic work, folks. At this point, you should be able to handle all the practice problems for section 6.7.